Hey AP Calc students, we are going to be going over a free response question from the year 2017. This is question number 3. So if you'd like, you can go to AP Central and look up this question. Again, 2017 number 3. You'll see a nice crisp image of it. I also have it printed right here, sometimes a little hard to read, but let's just jump in. This question is styled what I call a derivative graph, because that's what you're given, the graph of the derivative, and then you use all your calc skills to answer the questions that you're presented here. So let's go ahead and jump in. Question says the function f is differentiable on the closed interval from -6 to 5 inclusive, and satisfies the condition that f of -2 is equal to 7. The graph above is f prime, or the derivative of f, and it consists of a semicircle, clearly seen here, and 3 line segments. That's what you're given, and now let's jump in and see what they want to know. Question A says, find the values of f of -6 and f of 5. This is a pretty typical question for this style, and what they like to do is see if you can make the connection between the geometry of the graph and the integral representations. So I'm going to slide this over a little bit. I'm going to put in a little bit larger picture here for us to work with here, and this is the diagram we have. So you can see we're going from -6 to +5 over here. That's what these values are. I'm going to write those in here. So this x value was -6, and this is all the way over here at 5. And this value right here is -2. So the question is asking, what is f of -6? And notice that in the question it's given that f of -2 is 7. Now they seldom, if ever, give you information you don't need. So we're going to need that f of -2 is equal to 7. So right away what you should be anticipating here is if they give me the graph of the derivative, a skill you should know is that integration is represented by area under the curve. So we're going to integrate the derivative and then get the original function, and we're also going to use geometry. So since they want to know f of -6 and they gave us f of -2, we're going to zero in right here on this. So I'm going to jump in for part A. I'm going to take advantage of the fact that I know that if I were to integrate from -6 to -2, the derivative, I would know by the fundamental theorem that that would give me f of -2 minus f of -6. And that I also know by geometry I could figure this out because they gave me a pretty nice little right triangle right here to deal with. So if I just go up here and I say, well, I'm just going to make a little right triangle right here, take advantage of my knowledge of geometry, and it's going to be 1/2 base times height. Well, that's 2, and this distance here is 4. So 1/2 base times height, the area right here is 4. Half of 4 is 2, 2 times 2 is 4. So I'm going to put a 4 there, and I'm going to circle that. And I'm going to put the area is equal to 4, and I'm going to bring that down here. So I know that by geometry. Now, given in the problem here, they said f of -2 is 7. So I'm just going to say, well, 7 minus f of -6 is equal to 4, which is what they were asking for in the first place, f of -6. I'm going to add that to the right side of the equation, bring over the 4, and it looks like I get 3 is equal to f of -6. And I've just answered the first question. Okay. Now, the next part of part A says to figure out what f of 5 is. Well, that's way over here, f of 5. Well, to figure out f of 5, the only information I now have is they gave me f of -2, they gave me f of -6. So if I use the same approach, I'm going to have to go all the way from -2 to 5. No problem, I can handle that. So let's jump in there, and we're going to integrate from -2 to 5, again of f prime of x, and using the fundamental theorem, we're going to say that is f of 5 minus f of -2 is equal to, and now we have a little more geometry to do. This is a little more difficult. We have a semicircle right here. So if we jump in right here, we've got a semicircle right there, and it looks like the semicircle has a radius of 2. So if I said, just looking at the semicircle, I know that the area of a circle is pi r squared. This radius is 2, so the area of the circle is 4 pi. However, it's only a semicircle, and the semicircle is below the x-axis, which has to make the area negative. So 4 pi was the entire circle. It's only half of it, so it's 2 pi, and below the x-axis, this is going to be -2 pi. I'm going to write that there and circle it. So I know that this entire thing has to equal -2 pi, or just this part of it. We're not quite done. And then I'm going to have to add to this area of this triangle right up here. So let's see what we have here. This point here was 2, so the length right here is 3. And this height right here, I went over 3 and up 2. So my height right here is 2. 1/2 the base times the height. 2 times 3 is 6. Half of that again is 3. So it looks like the area of this is 3. So those are my 3 areas. All right, so I have a 4 and a 3 on the top and -2 pi below. So the area, now I'm integrating from -2 to 5. I have area above, area below. I'm going to write that as 3 minus 2 pi. Okay, non-calculator question, this is fine. So now we'll just jump in with what we know. From earlier in the question, they told us f of -2 again was 7. So I get f of -5 minus 7 is equal to 3 minus 2 pi. Let's add that 7 over, and I get f of 5 is equal to 10 minus 2 pi. There we go. Part A is finished. Let's move on. Part B says, on what intervals of f, the original function, on what intervals is f increasing? Justify your answer. Well, whenever you hear increasing or decreasing, that's a key word. That should make you think, well, I need to investigate the derivative to tell me what the original function is doing. Derivatives are positive, then the original function is increasing. Derivative is negative, original function must be decreasing. So let's jump to the graph of the derivative. We can clearly see positive and negative from here. So I'm going to scoot this up just a little bit, make sure we don't run out of room. And we'll look at this the enlarged picture we have right here. And if we look clearly here, it looks like from -6 to 2, we're above the x-axis. So for part B right here, I'm going to say, well, it looks like that the first derivative is positive over these intervals. It looks like from -6, and if we go all the way to 2, 2 is where, not including -2, I should say, we are positive. And then we're below the x-axis, and then we return to being above the x-axis from +2 all the way to 5. So there's the intervals where the derivative is positive, but the question is wanting to know when is the original function increasing. Well, there's where the derivative is positive, so we make a slight adjustment, and we say f is increasing. F is increasing on the intervals -6 to -2, and we can go ahead and include -2. That's acceptable for increasing and decreasing intervals. And I'll put a comma, and it's also going from 2 to 5. So the small adjustment I make, stating what's happening in increasing and decreasing, is I change my parentheses to brackets. And that is the end for letter B. Now let's move on. Part C. Part C says, find the absolute minimum value of f on the closed interval from -6 to 5. So in order to figure out the absolute minimum, you should be thinking critical numbers, critical points give us our peaks, valleys, flat spots, that type of thing. And in order to get your critical numbers, you have to set your derivative equal to 0. And then since it says absolute minimum, we're going to have to find our check our endpoints too. So once again, we're going to investigate the picture. Let's slide this down a little bit. So if we investigate the picture, we can clearly see that we have critical numbers that are at -2 and +2, and it looks like 5. That's when our critical numbers are equal to 0 or undefined. And so in order to set this one up, you should be thinking, well, in order to find my critical numbers, I'm going to find the derivative of x, and I'm going to set that equal to being undefined, and I'm going to set that equal to 0. So, but I have to use the graph. So when I look at the graph, the function is never undefined, so I don't have any potential points there. I look at where it is 0, and it definitely looks like it is equal to 0 at x is equal to -2, 2, and 5. So those are my critical numbers. It also turns out that 5 is an endpoint. I also need to check -6. Now I'm going to do this part a little bit very thorough. This next little step is not necessary, but I like to do it for a complete understanding. And so what I'm going to do is I'm going to actually do my interval test, which is a common approach here. I'm going to say, well, it looks like in the interval from -6 to 5, we have these critical numbers, -2 and 2. Now what you should also notice is that your critical numbers came from the 0 side, so these are going to be flat spots. These aren't cusps or corners, which would have occurred from the undefined side. So what I want to do is I just want to test the interval and just see what's going on. So remember, when you test your interval, I'm going to see what's going on with the value of the derivative to tell me what's going on in the original function. So between -6 and -2, if we just look at the graph, the derivative is above the x-axis or positive, and that tells me that the original function is increasing. Between -2 and +2, the derivative is clearly negative, which tells me the original function is decreasing. And between 2 and 5, the derivative is positive, and that tells me the original function is increasing. Now the reason I like to do that is it's already told me the question is looking for the absolute minimum. Well, if that's the case, there's no way that it can be at -2 or at 5, because the function's increasing to those flat spots. So even though I have to check these, I already can throw out -2 and 5. But that's just a little extra thing to be looking at when you're doing the problem. So now what we need to do is we're going to have to investigate here and figure out, okay, well, what is going on at -6? We're concerned about that. What is going on at -2? We're concerned about that. What is going on at f of 2? And what is going on at f of 5? Okay? Now, like most AP questions, much of the answers are going to be a part of previous work. And so let's see what's going on. Well, at f of -6, that was right here. That was actually the first thing we solved. That's equal to 3. F of -2, actually given in the question, that is 7. F of 2, we do not know, but f of 5 is 10 minus 2 pi. Now, I'm just going to check here. It looks like 2 did have potential because it was decreasing into it, so I am going to have to check this. Now, the nice thing is, the same strategy I used on part A, I'm going to use to figure out what f of 2 is. So I'm going to do a little extra work here and just set up another integral. So based on my picture, I'm going to integrate from 2 to 5, and I notice that in the geometry, it's equal to 3. So we should be able to set this one up pretty easily and get our answer here. So I'm going to say, well, I know that the integral from 2 to 5 of f prime of x dx is equal to f of 5 minus f of 2, and by geometry it equals 3. Now we also know that in the question, we know that f of 5, I should say, from part B is 10 minus 2 pi. And so I'm going to say, well, 10 minus 2 pi, I'm going to bring the 3 over, minus 3 is equal to f of 2. So 10 minus 3 is 7. I get 7 minus 2 pi is equal to f of 2. And that's what I need right here. So now I have the 4 points I can check. I just have to see which one's the smallest. So if let's approximate here, 2 pi is 6.28. 10 minus 6.28, we already knew -2 and 7 were not an option, but that's a larger number. And so I just need to check it, a larger number than 7 minus 2 pi, so it's not 5. 7's bigger than 3, it's not 7. So let's just compare 3 and 7 minus 2 pi. 7 minus 2 pi is between 0 and 1, so it looks like this is our winner right here. There's where our absolute minimum is. And so I would say absolute minimum occurs at f of 2, which is equal to 7 minus 2 pi. All right, and there's part C. Now, the last part says, let's find the second derivative at -5 and the second derivative at 3. Okay, we got some room over here I think we can use. So I'm going to look at part D. So part D, it wants to know f of -5. Sorry, f double prime of -5, or the second derivative. Well, since they gave us a derivative graph, asking you the second derivative is like asking you the first derivative of this graph. And when you think first derivative, you should be thinking slope of a tangent. And so I'm going to just focus in on this graph right here, and it wants this at -5. So here's what you're supposed to put together. -5 is right here. That's this x value, -5. And it wants to know the second derivative, or the first derivative of the first derivative. And a derivative is the slope of the tangent. Well, in -5, this interval is linear. So the tangent to a linear function is itself. So the slope of the tangent is the slope of the line. So at -5, I'm just trying to figure out the derivative right there on the function. It's just going to be the slope of that line. So if I passed Algebra 1 and can calculate a slope, I can do this one. So all I'm going to do is say, oh, well, f prime at -5, that's going to be the slope of the tangent right here. So I'm just going to do Algebra 1 slope. So difference in y over difference in x, I'm going to use the point at -6 first. So I'm going to say, well, that's the difference in y would be 2 minus 0 over -2 minus -2. So it looks like I get 2 in the numerator. And in the denominator, it looks like I get a -4. So it looks like I get -1/2. Makes sense with my diagram. It should be negative. Okay? All right, so that was the first part of part D. Now the second part would like to ask, or asks, what is the second derivative at 3? Or what's the first derivative of this picture, this graph at 3? Well, in this picture, if you go to there, you should notice right away we've got a corner. Not a 90-degree corner, but we usually call those a corner because we have two lines intersecting each other. And you would look at that and you'd say, well, that's undefined there. It's not differentiable. It's not differentiable at 3 because the slopes of the tangents don't agree. It's not like an upside-down quadratic. These are linear and they're coming to a point. So you could right away conclude, you could say, oh, well, that does not exist. And your reasoning would be they disagree. Well, that's not going to get you your full points on the AP, so you have to elaborate a little bit more, and you'd say, well, since a derivative is defined by limits, I'm going to approach 3 from both sides and show that they do not equal each other. So what I'm going to do is find the slope of the tangent at 3 approaching from the left, and I'm going to approach it from the right. So if I approach from the left, I'm just going to find the slope of this line right there. And so I'm going to say, well, as I approach 3 from the left, I'm going to calculate my slope. I'm going to say, well, that would be, again, the difference in y over x. I'm going to use 2, 0 first and 3, 2 second. So the difference in my y values would be 0 minus 2. The difference in my x values would be 2 minus 3. And I would get -2 over -1, which would equal 2. So it looks like approaching from the left, the slope is 2. Now let's approach from the right. The limit as x approaches 3 from the right, let's do that slope. I'm going to use the first point again, working left to right. So the difference in my y values is going to be 2 minus 0 over 3 minus 5. So it looks like I get 2 over -2 or -1. So you can see that the limit from the right does not equal the limit from the left. And so I could say the limit as x approaches 3 from the left does not equal the limit as x approaches 3 from the right. Therefore, second derivative at 3 does not exist. All right, and there it is. 2017, question number 3.